I was checking the audio. Okay, so grades, exams are graded and returned. I guess technically I wouldn't have to collect attendance today because all I could do is just, like, these are the ones that aren't here because I didn't give them their exam, but yeah. Okay, so for once, we're really caught up in here in terms of grading. We didn't have lecture on Monday, but I pre-recorded that lecture. I counted everybody present in class for that. So I gave everybody like an attendance grade for Monday. All the outstanding homework is graded. Homework 5.7 was due today, so homework 5.7 is the only one that isn't graded because you all literally just turned it in. Homework 6.1 is going to be assigned today. It's going to be due on Friday. I'm going to give you a homework 6.2, but it's not going to be due Monday, okay? Because it's a little bit longer, but basically what's going to happen is on Friday, so let me just take a step back. Today we're going to do deflection problems involving beams with single moment functions, and then on Wednesday, or on Friday, we'll look at multiple moment functions. I'm going to give you a multiple moment function homework on Friday, but then on Monday, we're going to have a separate lecture that's just tips and tricks to make that homework easier, and to make that task easier, because there's tricks that you can do to make that problem a lot smoother, okay? So yeah, everybody good on that? And then you all just submitted your first submittal on the project. I don't know if you haven't graded that, but I think that'll go a little bit faster, so. Because I already told you, I'm basically going to be checking each truss for that checklist, and then I'm going to review your write-up. So I think that'll go pretty quickly. Okay, everybody good? Okay, so I'm hoping everybody watched did everybody get the code? Okay, so I'm hoping everybody has watched in detail my pre-recorded lecture on beam deflection, because I know everybody watched that, right?
Yes. Absolutely.
I believe everybody in here 100%. I'm just
Absolutely.
Okay. All right. I don't know why that's okay. All right. So, but I'll give you the quick recap. Okay. So I have here on the whiteboard this expression, which I'm hoping by now is familiar because we literally just talked about it a couple minutes ago. This is how we compute deflections in trusses. Okay. Now, for beams and frames, the idea would be that we would do something similar. That we would say, okay, let's sum something up. And maybe what we'll do is we'll sum big ML over, or little m big ML over maybe EI, since it's a beam. Okay. Now, this expression would be completely fine if the moments were constant. But how many moment diagrams have we drawn that go, some weird shape like that? Like, moment diagrams are not constant. They're variable functions along the span. So instead, we really can't use this, okay? So instead what we do is we use a differential approach. Instead of summing these fractions, what we're going to do is, instead of MML over EI, we're going to take little m big M over EI and integrate it. And instead of summing up these fractions, we're going to sum up these integrals. Okay. Now, before everybody gets worried about having to do a bunch of integration, the integrals that we're going to be doing are largely polynomials. And the nice thing about that is your wonderful Casio FX 115ES Plus or similar scientific calculator will do a lot of these integrals for you. These are really, really straightforward integrals. To give you kind of an example, you'll have something like this, which, is something I know that you all know how to do. Everybody in here can integrate something like that. And so that's about as complicated as it's going to be. We're not going to have any integrals of tangent of e to the x to the 4. It's not going to be any stuff like that. Okay, it's going to be really, really basic stuff. So if you can do that, you're going to be good. Okay. All right. So like I said, in order to compute beam deflection, we're going to be using the following expression. So we're not going to be summing up a fraction. We're going to be summing up some integrals. Now, we'll use the same idea whether or not we're looking at deflections or we're looking at rotations. And so if I have a beam that's deforming, if I look at a given point, I'm going to be interested in how much that point moves up and down and how much that point rotates and twists. Okay, if that makes sense. All right. So what goes into this expression? Well, we're going to have some little m's and some big M's. Now, just like with trusses, the big, like capital F results, this was the real forces inside the truss members. Big M is the real moments inside the beam. So the big M's are going to be my moment functions. I gave you all a homework assignment that was due today where you had to derive moment functions. There was a reason that I wanted you to do that because we're going to need that, okay? So we need real moment functions. We also need virtual moment functions. Now, the same idea applies with the virtual structure as it did with trusses. We take the original structure, we remove all the loads, and we replace them with just a single load. We put that load at the point of interest in the direction of assumed displacement with a magnitude of 1. Now, if we're looking for deflections, we place a unit force. If we're looking for rotations, we place a unit moment. Okay? Does that make sense? Now, we also have our Young's modulus, which is in KSI, and we have our moment of inertia, which is in inches to the fourth. Y'all remember how to compute moments of inertia? Like if it's a rectangle, BH cubed over 12. Y'all remember that from ENGR 216? Now, if you're somewhat aware of what's going on here on the slide, you'll see we have a unit inconsistency. I talked about that in the pre-recorded lecture, how we have foot kips here, but we have KSI in inches right here. So whenever we're performing a deflection problem, we have a unit conversion factor that we need to apply. So for deflections, the unit conversion factor is 1728, and where that comes from is just the number 12 3 times, like 12 times 12 times 12. Because what we have to do is convert feet to inches, but we have to do it 3 times for deflections. We only have to do it 2 times for rotations, so the number is 144. But rotations, whenever you do the math, rotations end up like, if it's unitless, they're in radians, and they end up being really, really small for most structural analysis problems. So to make the numbers a little bit more digestible, we'd like to express them in degrees. So I'm throwing in the 144 and then a 180 over pi to get that number into degrees. So when we perform deflection calculations for beams and frames in US units, the deflections will come out in inches, the rotations will come out in degrees. Okay, so yeah, so there's a very, very, very small amount of memorization there. Okay, today our goal is going to be looking at singular moment functions. In other words, beams where you only need a single moment function in order to define the moment diagram. And those are the only problems that we've derived moment functions for this semester. So let's talk about that, okay? Let's look at this problem, okay? So this problem is a beam that has support right here. This is really important, okay? I have a beam here, I have a support here, and I have a support here, okay? So let's think about what the shear diagram and the moment diagram would look like, okay? So what do we have? We have this like quadratic shear diagram, a jump, linear, jump, quadratic shear, right? And then the moment diagram, I'm going to have some sort of cubic function, parabolic function, cubic function, something like that, right? So how many separate curves define the moment diagram? I propose that the answer is 3, okay? Because there's going to be a cubic function here, a parabola here, and a cubic function there. Now, what I'm doing right now is I'm sort of working ahead and I'm saying, okay, if I draw the shear diagram, it looks like this. If I draw the moment diagram, it looks like this. So in order to answer that question right now, I'm having to almost like draw them and look back. But that's a lot of work, okay? So an easy way of figuring out how many moment functions a given problem is going to need is to imagine breaking out the samurai sword or lightsaber, but imagine moving this line across the beam. And once you pass through some sort of interruption in your loads, you're going to need a new moment function. So let me explain what I mean. So here's my little folder. I'm going to cut a section and I'm going to move it over. So if I cut a section right here, look to the left, what do I see? I see a triangular load, right? Now what if I cut a section right here. It's still a triangular load, right? In fact, from A to B, it's a triangular load if I cut a section and look to the left, right? The whole time. But what happens when I get right there? Whoop, now things are different, okay? Because now I've got this reaction here, and I have a distributed load right here. So cutting a section from A to B, looking to the left, I have a triangular load. But cutting a section here, looking to the left, cutting a section between B and C, looking to the left, I've got a triangular load, I've got a distributed load, I've got a point load right here. Okay? So now it becomes a new function. So here's sort of what I'm getting at. 1, there's an interruption 2, there's an interruption 3. And I propose that by doing that, this beam needs 3 moment functions. Okay? Does that make sense? So the first set of problems that we're going to do together is problems where it's 1. We only need 1 moment function. On Friday, we'll discuss multiple moment functions, and we'll even discuss it on Monday as well. Friday, we'll do a problem. Monday, I'll talk about easier ways to do the problem. With me so far? Now, the real structure is the original loads. The virtual structure. Let's think about the virtual structure, everybody. So the virtual structure, we kick all of the loads off, and we place a single load, either a unit force or a unit moment, right? That's what the virtual structure is. Okay. So would you agree that the virtual structure is only going to have concentrated forces or concentrated moments? That's all it's going to have. The virtual structure is not going to have any distributed loads. It's not going to have any triangular loads. The virtual structure is just point loads and point moments. So here's a point load, here's a point moment. This is what the shear and moment diagram looks like when you have a point load, right? Like we have a jump in shear, change in flow. What about a point moment? No change in shear, but we have a jump in the moment diagram. Right? That's what they look like. Now I want to look at the moment diagrams. Do you see any patterns here and here? And I know it's a high level question for a Wednesday morning. I'm going to sort of answer it for you. These are all lines. Okay? I know that sounds funny, but I mean this because I've taught this class a lot. I'm telling you what's going to happen. I can't tell you how many exams I've graded where somebody's investigating a virtual structure and the moment diagram on the virtual structure has some curvature to it. It can't, okay? The virtual moment diagram, especially for determinate structures like this, well, really for any structure, is going to be linear, okay? An easy way to find the virtual moment functions is to recognize that they're going to be lines, okay? So there's 2 ways you can do that. You can break out the old samurai sword or lightsaber, which can be tedious, or what about some basic geometry? How do you find the equation of a line? Well, you can get the slope of the line, but don't we have the slope of the line because the slope of the line is the shear? And then once we have a point, y minus y1 equals the slope times x minus x1, or in this case, y is the function of interest. So we can do this a lot faster if we just use point slope. Okay, and don't worry, we're going to do some practice on this. Okay, if we graphically construct the shear diagram and the moment diagram for the virtual structure, then we can get these moment functions with a whole lot less algebra. Trust me, it will be a lot simpler. Okay, and in order to explain that, and I guess one other point is that this would work for the virtual structure, but it would also work for the real structure if the real structure had a bunch of point loads on it. To explain this and to work through this process, I want to do a problem, okay? So I have a cantilever beam here. I want to spend this lecture finding the displacement at A, and I want to find the rotation at A, okay? And so we're going to do this problem start to finish today, and then I have a homework that's very similar to this, okay? What I want you to do is walk through me on this. We're going to take it one step at a time. Okay, let's just get into it. Okay. Now, couple things that are on this problem that haven't been in beam problems that we've been talking about thus far. Okay, hold on. Why is my pen not registering? Come on. There we go. I was about to say. That would not be good. Okay. All right. So a couple things to just sort of note before we go down the rabbit hole here. First off, for shear and moment problems, I did not give you E. I did not give you I. Okay. I have for this problem because you need those values to compute deflections. Okay. Or another way of saying it is at the moment which we start talking about deflections, no pun intended there, but whenever we start bringing up deflections and rotations, the terms E and I have to be relevant. Either you need E and I to solve for the displacements, or for a given displacement, you can figure out what E and I needs to be. And I bring up the latter problem because that's design. How do you size a beam? Well, size it where it's strong enough and stiff enough to resist the loads. So your homework assignment, instead of giving you I, I'm going to have you solve for I. Okay? So just keep that in mind. Okay. Now we're going to determine the the vertical displacement and rotation at point A on the beam shown below using the method of virtual work. Going back to my example before, okay, how many moment functions do we need to fully define the moment diagram? Cut a section, walk it over. If I just cut a section here, look to the left, I got a beam, distributed load. Whether I'm over here, over here, over here, it's a beam with a distributed load. So how many real moment functions do I need to fully define the moment diagram? One. So I'm going to break out the samurai sword or lightsaber. I'm going to cut a section right here. Now, which direction would you like me to look? Left or right?
Left.
Left. Let's talk about that. Does it really matter which direction I look? At the end of the day, no. Like, the beam doesn't care which way we look. The answer is the answer. But my laziness cares. If I cut a section and look to the right, I need the reactions. If I cut a section and look to the left, I don't have to solve for them. I'm lazy. So I'm going to cut a section and look to the left. Okay? All right, so first thing we'll do, all right, so real moment function. We're going to cut a section, we're going to look to the left, okay? So when I cut a section and look to the left, that's going to be my section, okay? Now, how long is this segment? Well, we're trying to write a function. We're trying to write an equation that predicts our moment. So how long is this segment right here? X.
5 foot.
Right? It's going to be X because, like, what we want to be able to do is we want to be able to plug in any value. So it could be 5, 10, whatever. So, and here's the other thing I want to do. Hold on. Let's do something off to the side. Do something off to the side. Here's the beam. How long is this beam, by the way?
15.
15. And what's the load on it? What was it, 1.25 or 2.5 kicks per foot? All right. What reactions are we going to have here? We're going to have a vertical reaction, right? We're going to have a moment reaction. Are we going to have a horizontal reaction? No. Can somebody tell me what's the shear diagram going to look like? Like, what is it going to look like? I'm not asking for numbers. Just tell me what the shear diagram is going to look like.
It's gonna like linearly go down and then jump up to cut.
Start at 0, distributed load, go down, and then that's going to bring us back up, right?
That's what I said.
And so, I'm agreeing with you. Is everybody okay with that? Okay. So somebody else, tell me what's the moment diagram going to look like? I'm not asking for values, just tell me what it looks like. Parabola, okay? What's it, but okay, this is the axis, right? So is this area positive up here, positive or negative?
Negative.
Negative. So tell me what the parabola is going to look like. Is it going to go like that? Well, hold on. We're going little to a lot. Little slope to a lot of slope. Does that make sense? Okay. Okay, that's what the moment diagram is going to look like. Does everybody get that? Just keep that in the back of your head. All right. So let's go back here to the screen. Okay, so this is 2.5 kips per foot. Tell me what to do. Should I collapse that into a point load? Everybody help me out here. Come on now. All right, so if I collapse this into a point load, how much is that point load?
2.5x.
How far from the section cut? And then we have our shear, which is down, which we're actually not going to derive the shear. I don't care about it. I'm not using the shear in this expression. I don't see any V's here. I just see M's. I'm going to ignore the shear. How do I derive that M? Tell me what to do.
Moments at the cut.
There we go. I'll do it like this. Some moments at section 1, looking left, equals 0. So, what do we have? We have 2.5x times x over 2 and m. So, what is that? That is m plus 1.25x squared. So does that mean that m equals minus 1.25x squared? This something that I'm going to put here, and this is going to become relevant on Friday, is I'm going to put this. In other words, this is valid from x equals 0 to x equals 15. Okay? Because this is the left-hand side of the beam where x equals 0. This is the right-hand side of the beam where x equals 15. Okay? Okay? Now, is there a simple way that we could test whether or not this equation is right? Well, that's one way. And that is a fine way. Here's another way. So there's that. Insert. Does that look right? Looks right to me, doesn't it? So you could just plot it in Excel and see if you get the right answer. Okay? Which we did. So, okay. So I'll put that up here on the board here. M equals minus 1.25 x squared, valid from 0 to 15. Okay? Is everybody with me on that? Okay. Now let's do a virtual structure. I'm going to do the function derivation this time. We'll do the line stuff on Friday. We'll keep it simple today. So this virtual moment function is going to be for the vertical deflection at A. Okay, so I'm going to call this M delta. Okay, and how are we going to do this? So let's go to our original structure. So that's our original structure. Okay? Now the original structure had this distributed load on it. I'm going to kick those loads off. Okay? I'm interested in finding the deflection at A. So I'm going to place a vertical load right here of 1.0, just like we did with trusses. Now you tell me, do you think this point's going to deflect upwards or downwards? Down. I heard down. So we're going to place this load downward. Okay? We're going to now cut a section. Look this way, and let's see what we get. So, we cut a section. All right. 1.0. We have our shear. Remember, if we cut a section and look to the left, downward shear, moments like that. I'm going to use little letters now, so we'll use a little v. And a little m there. And let's see if we can derive our moments. So, by the way, how long is that again? X. Okay. Doing good on time. Okay. So we're going to sum a moment, or some moments, at section 1-1, looking to the left. So what do we have? Now, I did the first one. You all help me with this one. What moments do we have and what side do we put them on? All right. So what generates moment at this section? M, which goes left or right?
Right.
Right? And what else?
1 times X.
1 times X. So we have 0 equals M plus X. We have M is minus X. Valid. 0 to 15. I'm going to rewrite this, though. I'm going to call this M delta, because I'm going to have a different M for the rotation. So, I need to go ahead and make that a bracket. Bless you. Okay. Okay. So now I have everybody with me on that? Okay. If you understand that, the actual process of doing this is really, really easy. Okay? This is the hard part. The hard part is getting these. The actual virtual work is straightforward. Let me show you. Okay, so let's do the method of virtual work. Okay, so what do we have? We have big M. All right, let's do it in order. So little m is minus x, big M is minus 1.25 x squared. Okay, and let's, if this is the case, in our expression, we're going to be integrating little m times big M. So somebody help me out. If this is little m and this is big M, what's the product of those going to be? So negative x times negative 1.25 x squared. A negative times a negative is a positive 1.25 x cubed. All right. I'll also, let me do something else. Let's put some units on this. Sorry, that scooted away from me. So this big M, this is going to be in foot kips. Like whatever answer we generate is going to be in foot kips. Now, the moment comes from a unitless load. So if you take a unitless load times a moment arm, technically these moments are in feet, but that doesn't like really matter all that much. But I think what I really want to make sure that you're aware of is that E is 20,000 and I is what, 1,500? The big thing I want you to be aware of is that this is in KSI and this is in inches to the fourth. Okay? So in order to compute this deflection, okay, so how do we get the deflection at A? How do we do that? Okay? Well, ultimately what we're doing is we're summing up these integrals, but we only have one integral. Okay? So we'll just call this the integral of, little m, big M over EI dx. Okay? So let's see. Let's see if we can chug this out. All right, so we got a fraction. Okay. So on the bottom of that fraction is EI. On the top of that fraction, we have dx. Now, what are my limits of integration going to be?
0 to 15.
0 to 15. So we'll write that as x equals 0 to x equals 15. And that's my integral. Okay? Now, the one thing I'm missing is a unit conversion factor. I'm calculating deflections. So what I have to do is I have to multiply this whole thing by 1728. And suddenly, this becomes a Math 229 problem. So tell me what I can do with all these constants. What did Math 229 teach me I can do with all these constants?
Put them outside the integral.
Factor them out. So let's do that with every one of them. So that means I've got 1.25, 1728. Sorry. So if I pull out all these constants, what am I left with? I'm left with that, aren't I? Just an integral from x equals 0 to x equals 15 of x cubed dx. I have to believe that's something that you don't need me to show you how to do. Is it? Again, you can plug that into your Casio FX115 ES Plus or similar scientific calculator right now. It will yield 12656.25. And in case you want me to do that, boom. I'm hoping that's simple, but, right? I mean, because we're just integrating x to the third from 0 to 15. So the integral of x to the third is x to the fourth over 4. 15 plug in top number minus plug in the bottom number. Boom. So what is this? When you chug all that out. You don't have Casio FX115 ES Pluses or similar scientific calculators. 0.911. Do I have a second on that?
Yes.
So therefore, what that means, point A on this beam bends downward and it deflects. .911 inches downward. That's not too bad, is it? I mean, you tell me, is that pretty straightforward? Okay. Now, we're not going to have time to do the rotation one, but since I've gotten requests to give answers in the back of the book, here's what I'm going to do. I'm going to give you a couple of answers, and I want you to be able to do this on your own. So, that's your moment function. This is one of those, I want you to work on this on your own. And the rotation is that. I'm giving you the answer. You all can do the work. And whether you'll do it or not, I don't know, but you do have a homework that's due on Wednesday, that all this will, or sorry, due on Friday, that all it will do is make this a little bit easier to do. Sound good? Then again, I know you have a materials exam from that horrible professor tomorrow, so you'll have to deal with that. That's all I got, everybody. I'll see you tomorrow. Well, most of you, I'll see you tomorrow.